Good morning, everyone. Just I'll brief it like what we have discussed in yesterday's class, so that it will be easy for us to continue today's class and to understand the concepts. So now, first coming to yesterday, we have discussed what is a bucket. So instead of storing one record at one address in one address inside your file, here in case of a bucket, we are trying to store more number of records at a given address. Okay, that's what basically a concept of bucket we have introduced yesterday. So each and every bucket will be having a unique address. The capacity of a bucket is wherein you can store more than one record inside a bucket. So each bucket will have a unique address. So that's what basically we have seen what exactly a bucket is. Okay, a bucket describes a block or record sharing the same address that is retrieved in one disk access. So why basically we're moving to the concept of buckets is bucket is treated as a block. So what you will be having inside a block will have more than one record, correct? So whenever you are accessing the records from your hard disk or whenever you are writing the data back to your hard disk, so you'll be fetching more than one record or you'll be writing more than one record to your hard disk instead of fetching one record at a time. Okay, so that's the concept of bucket yesterday we have discussed. When a record is to be stored or retrieved, its home address is determined by hashing. So like in the previous example what we have seen here also, whenever you want to store a record or whenever you want to search for a particular record, the key value of the record should be given as an input to the hashing function. So this hashing function will give you or it generates the home address. So you need to go to the appropriate home address or you need to go to the appropriate home address where the bucket is stored. Then you're supposed to add your record or you're supposed to fetch the record from that bucket. Now here also here we cannot always ensure that it doesn't leads to collision or collision doesn't happen or it's free of 100% collision free. Definitely. For example, let me consider I have a bucket whose capacity is to store 3 records. Now, for example, let me consider I want to store the records. Say first record I want to store and I'm going to give the key value of the first record as an input to hashing function. It generates the same address. I'll store that record in that particular bucket. Second record I want to store, the key value of the second record I'm going to give as an input to your hashing algorithm. It also generated, assume that it has also generated the same bucket address as first record where I've stored. Third record also I stored. Suppose say when I want to store the fourth record, when I'm giving the key value as an input to my hashing algorithm, assume that the fourth record also has generated the same bucket address where your previous 3 records are stored. Now here we have made an assumption that capacity of each bucket is 3 records. Now definitely fourth record I cannot store. Means here also we cannot always ensure that there will not be any overflow because the capacity of the bucket you have increased to be more than one record. Okay, when a bucket is filled, we still have to worry about how do you handle this particular overflow records. This overflow problem is definitely present in case of a bucket also, but it occurs much less often than when each address can hold only one record. So in the previous class we have discussed, we have seen a bucket capacity was able to store only one record, right? Here the particular overflow or the collision will happen less frequently. That is what basically we have used. So yesterday I have shown you, like say in this example I have 2 buckets. The first bucket address is 214, second address bucket address is 215. Capacity of each bucket is 3 records. You can also take increase the capacity of each bucket also. So all these concepts we have discussed here. This is for example the key values, and these are the home addresses generated for those key values by using some appropriate hashing function or an hashing algorithm. And this is how your buckets will look like. So this is a 0th bucket. Capacity of this 0th address of the first bucket, and capacity of this bucket is 3. Similarly, second bucket capacity is also 3. Third bucket, fourth bucket, all the buckets capacity they can hold 3 records, and each bucket will have a unique address like this. Now, effect of buckets on the performance. So like in the previous class, we have discussed something called as a packet density. So what is this particular packing density is nothing but, suppose given your file in the previous concept, whatever we have discussed, suppose given a file and you have a set of records that has to be stored inside the file, how these particular records are distributed inside your file. Whenever you're storing these records inside your file, how the records are being distributed? Are they randomly distributed, or how densely your file is packed. To know how densely your file is packed with the records, we use a concept called as a packing density. So here also, in order to know that how densely my file is being packed with the records, we use a concept called as a packing density in case of a buckets. So in case of a buckets, how do you calculate the packing density? So capital N is nothing but total number of buckets you have, and number of records we want to put at each address in B is the bucket size. Like capacity means how many records you can store per bucket. How many records you can store per bucket is nothing but given by B. N is nothing but the total number of buckets what I have, and R is nothing but number of records what I want to store. Okay, given these three parameters, packet density can be calculated as R divided by Bn. So R is nothing but the number of records which I want to store inside the buckets. B is nothing but like how many what's the capacity of each bucket. N is nothing but total number of buckets. So by using this packing density, I can check like how densely my file is packed with the records. Okay, so this is basically how we do it. And through the packing density does not change. Suppose say here in the last case we have seen that suppose if we increase the capital N, or if you increase the small r, okay, the packing density was changing. When N and R, when the packet density was increasing, in the last class or in the one of the slide we have seen that the packing density has increased linearly. You were able to see that the number of overflow records also was linearly increasing. But in this case, it doesn't mean that suppose if a packing density goes on changing, for example, say N value will be changing, R value will be changing, B value will be changing. So definitely whenever you are going to change these values N, B and small r, okay, say for example you want to reduce the number size of the file, or you want to increase the number of buckets, and say for example you want to increase the number of records what you can store inside the bucket. So whenever you are making some changes with these particular parameters, definitely the overflow here, the expected number of overflow will get decreased dramatically. So it doesn't mean that whenever you change the parameters, say doubling the size of the block and reducing the size of the file, means that your overflow increases. No, because once you are reducing the size of the file, the bucket size you are increasing. Number of records that can be stored in the bucket you are trying to increase. That's the reason usually the number of overflow records will get decreased in this case of your buckets. Coming to the next concept is nothing but making a deletion. So in the earlier till there we have seen how to make an insertion, how to perform the search, how much time it takes whenever you want to perform a search operation, all those things. Now coming to the deletion, whenever you're going to make a deletion with respect to your hashing, how does your deletion works? See, deleting a record from a hash file is more complicated than adding a record. Okay, why is that? There are two main reasons why it is difficult. The slot freed by the deletion must not be allowed to hinder later searches. For example, say you have added the record at some particular address, and okay, and you basically want to delete that particular record. So even whenever you want to delete a record, what basically you do, the key value of the record which you want to delete, the key value will be given as an input to your hashing function. Hashing function will give you the address. You need to move to that particular address. Okay, whenever you move to that particular address, if a record is found at that particular address, you will delete it. Okay, suppose if the record whatever the home address the hashing algorithm has generated, if the record is not found at that particular address, then what do? You cannot stop there itself. You cannot stop is there. You have to check for the next successive location if the record is present or not. Okay, after you check for the next successive locations in order to check if a record is there, so that you have to delete. So once it is found, assume that you have deleted that record. Okay, so after deleting, assume that there are some more records present after that. Okay, so second time, say I want to search for that record which was following that deleted record. So whenever I want to search, now since I have deleted that record, when I go on searching the next successive location, I may encounter an empty space because I have deleted a record at that particular place. Whenever empty space is there, it means that end of the file. So my file gets terminated telling that search not found, even though records are present after the deleted record. Whenever it encounters a empty space, it assumes that it has reached end of the file and a record is not found, but still your record is there. Okay, the free slot by the deletion must not be allowed to hinder later searches. This is one of the problem. Second one, it should be possible to reuse that space. The space the record which I have deleted, that space should be utilized in order to add the records in future, right? So these are nothing but the two problems we are going to face while deleting the records. Okay, so now the question is, how do you overcome these two problems? Once you delete a record, these are the two problems you're going to encounter. How you're going to overcome that particular problem, right? So we use a concept called as tombstones. We use a concept called as tombstones to overcome that particular problem. So now, what does a tombstone basically means, or how do we make use of this particular tombstone? Okay, tombstone is nothing but we are going to use a special symbol or a special marker indicating that a record once was present there, but now it no longer exists there. In order to indicate that, you're going to use some special marker. After deleting a record, you're going to place that special marker in that deleted record position. Basically, it indicates that once upon a time a record was there, but now the record is no more existing. That special symbol, whatever you're using, it gives us a meaning that once a record was present there, but now that record no longer exists because that record was deleted. This is the meaning what your special marker or whatever the special symbol you are using basically is used to indicate. Okay, so this is the basically nothing but concept of a tombstone. Now let us see with an example how tombstones solve both the problems, as I told you that. So okay, insertion of the record is slightly different when using the tombstone. Let us see how do we do this with an example. So deletion, for example, assume that these are the records with the different key values what I have, and these are the respective home addresses I have. Now this is my file basically I have. So these records, whatever the home addresses they have generated, I'm supposed to insert those records into this particular file using a progressive overflow concept. So in the last class, we have seen how does our overflow, progressive overflow or linear probing or open addressing, okay, works. So now what do you do? Adams. What is the home address of Adams? 5. I'll go to 5. Okay. Since the space is free, no record is there, I'll insert that particular record there. Now Jones, 6 is the home address. I'll go to address 6, insert Jones, because no other records are there. The location was free. Now Morris, what's a home address generated? 6. I'll go to 6 now. 6 is being already occupied by some other record, that is John's. Now what do I do? So how does a progressive overflow, how do it operates? You're going to check if that home address is not free. You're going to check for the next successive location if it is free. So now we are going to check the next successive location. Since that particular location was free, we have inserted Morris there, right? This is how your progressive overflow works. Next, Smith. What's that home address it has generated? 5. I'll go to 5. So 5 is not free. It's filled up with some other record. So next I'll check for the next successive location 6. Yes, 6 is also occupied by some other record. I'll check the next successive location Morris. Yes, it's also been occupied by some other record. I'll check the next successive location. Yes, it's free. So I'm going to insert Smith here, right? This is how your progressive overflow works. Okay, now let us see, our main intention was how do we perform delete operation, right? So suppose I want to delete Morris. Okay, if I want to delete Morris, what should I do? I'll basically knowing, oh, I should give the Morris as an input to your hashing algorithm. So it generates, for example, 6, correct? If Morris is simple erase, okay, so I'll basically go here, it is not matching 6. I'll go check the next success. Yes, it's matching. I'll delete this Morris. See, after deletion of Morris. So the slash indicates that it's an empty location. Okay, it's an empty location. So empty slot. Okay, so now for example, assume that after deleting Morris, I have further more records after Morris. Now for example, say I want to search for Smith. So Smith, the address is 5. I'll go here. That Smith address is not found here. Check for the next successive location. It's not matching. Check for the next successive location here. So it's an empty. So whenever it is an empty, so basically it comes out of the program and it tells that yes, Smith is not part of this particular file. See, empty slot wrong, we can't find Smith. It tells that yes, it is an empty slot. It assumes that it's the end of a file and tells that Smith cannot be found. This is a problem we are going to face. See, after your record is being deleted, you have some more records after it. If you want to search for those some more records after the deleted record, it becomes very difficult. So how do you handle this particular problem? It's nothing but using a concept of or using an idea of tombstones. So replace the deleted record with a special marker indicating that a record once lived there no more exists, to indicate that. Okay. So what do? Once you delete any record, you're going to use some special markers. You can use any marker. Need not be always this hash. Okay, but you have to tell that wherever that a special symbol is there, you have to specify its appropriate meaning. It doesn't mean that it's an end of the file. Okay, a search must always continue when it finds a tombstone. Whenever the tombstone is there, your search should not stop there. It should continue further, but can stop whenever an empty slot is found. A search for Smith will continue when it finds the tombstone. See, since tombstone is there, we have written a code inside our code. Whenever we are writing a code, we need to write in such a way that whenever a search encounters a tombstone, it has to continue the search. It should not stop there itself. Okay, we have to that is incorporate all this particular concept when you are implementing the concepts in your program. Okay, only insert a tombstone when the next record is occupied or in the tombstone. If the next record is an empty slot, we may mark the deleted record as empty. Suppose after the deleted record, if you have some other records, then only the tombstone concept plays a very important role. Suppose say after the deleted record, if there were no records present after the deleted record, then definitely there is no need to insert, there is no need to make use of this concept of tombstone. Whenever an empty space occurs, you can just tell that that is the end of the file and you can terminate your program and you can make the decision that search is unsuccessful. Okay, so effective deletions and additions on performance. After a large number of deletions and additions have taken place, one can expect to find many tombstones occupying the places. See, suppose if you have a very large file, you have made too many additions, too many deletions. In order to not to hinder the further searches, we have introduced a concept of tombstone into that particular file. So after many additions and many deletions have been done and many tombstone occupied the many places inside your file. Okay, the home addresses, the records that are present from the home addresses, okay, will be very far from them. Okay, so whose home address precedes them, but they are stored after them, means it will be very far. The records which are not exactly stored at their home addresses will be stored at the addresses which are very far from their home addresses. When the records are stored very far away from their home addresses, definitely the amount of search length it takes whenever you are searching a record will be very much high. Means the search length, it is going to increase the search length since the records are being stored far away from their home addresses where exactly they were supposed to be, right? So there are three types of solutions how you can deal with this above problem. So what is that is, first one is localized reorganization. Whenever you make the deletion of the record, you try to make the changes locally within the file without affecting the file in a larger extent. That is one solution. Second one is global reorganization. See, for example, frequently you can tell that, see, after making additions, many addition, deletion, and end of the week, I'm going to reorganize all the records inside the file, so that the maximum number of tombstone I'm going to replace with an empty. Okay, or you can use some other hashing function. You can reorganize your entire file so that the searching the search length will not become too high. So this is one way you can basically overcome this particular problem. Third way is nothing but you can use different collision resolution algorithm. Okay, so now in the next session we'll be discussing which are the different collision resolution algorithm we have. These are some of the collision resolution techniques or algorithms, basically what we have and how it works. There are few variations on random hashing that may improve the performance. So what are they? First one is called as a double hashing. Second one is called as a chain progressive overflow. Third one is called as a chaining with separate overflow area. Last one is nothing but called as a scattered tables. So these are the alternative collision resolution techniques or algorithms what we have. So we'll look at each one by one, and we'll look into each and I will discuss how they work. Okay. Coming to your double hashing. What is your double hashing? Say for example, I have again as usual, I have these are the keys of the records. These are nothing but a key values, and this is one of the hashing algorithm or hashing function I have. So if I give this key values addends to this hashing function h1 of k, if I give, it generates a home address 5, John's, if I give for this H1 hashing function 6, Morris, Smith. Here, why the name double? We are going to use two different hashing algorithms. H1 of k is one hashing algorithm, H2 of k is another hashing algorithm. Now, what I'll be doing is same values, same key value I'm going to give as an input to the second hashing algorithm. It is generating and it's giving hashing address as 2, 3, 4, and 3. So these are the home addresses generated when I give these particular key values as an input to first hashing function. These are the home addresses what it is going to generate when I give these particular key values as an input to the second hashing algorithm. I'll basically making use of two hashing algorithms. And these are the home addresses. Now what do I do? Okay, so first what do I do? First I want to store, for example, Adams. I look at the first home address generated by the first hashing function. Yes, it was free. I have stored this record in this location. Now I want to store Jones. What is this address 6? Yes, I'll go to address 6. Yes, it's free. I'll store it. Now again, Morris, a home address is 6. I'll go to 6 here. 6 is being occupied, means 6 is being already occupied. If I want to store Morris, it becomes an overflow record. So now what I'll do is, since there is an overflow, I'm going to add the home address of the previous one 6 plus the home address what your second hash. Now I'm going to make use of the home address generated by a second hashing algorithm, that is 4. 6 plus 4 I'm going to add. 6 plus 4 gives me 10. I'll move to the 10th address in your file. Check if it is free. So if it is free, I'm going to store it. Now you may be having a question, ma'am, what if 10th location is not free? If 10th location is not free, then probably you need to change this particular both the hashing functions. You need to come out with some other hashing function. Suppose if number of cases are more, something like this, you need to come out with a different hashing algorithm. Instead of H1, H2, you can use something H4 or an H5 hashing algorithm, which uses a different techniques to calculate the home address. Okay. Now coming to the next record, Smith 5 I have. I'll go to 5. 5 is occupied. So what should I do? Add 5 plus 3, 8. Go to the location 8. Yes, since it is free, you store that. So this is how you make use of your double hashing in order to store the records. And why the name double hashing? Because here we use two different hashing algorithms. Okay. Coming to the second one, chained progressive overflow. So let us understand what is chained overflow with an example. See, these are your key values. These are the home addresses, the key values as generated by using some hashing algorithm. And this is your progressive overflow, means search length for this particular example using your progressive overflow. The number of average search length they've calculated as 2.5. For the same example, we are going to try to calculate the average search length, and definitely the average search length, if you're using this chain progressive overflow, is becoming less. Means you basically require less number of disk access in order to fetch the records. Yes. So now definitely we need to understand how this chain progressive overflow works. So this is your progressive overflow. How data will be stored in a progressive overflow. I need not repeat once again. Many times I've explained how you basically are going to store in a progressive overflow. Our main intention is to understand how your chain progressive overflow works. So now coming here, in case of a chain progressive overflow, here we have what's the Adams address 20. I'll go to 20, store Adams here. Here basically I have two fields here. This is one column I'm going to store my actual records, and the second one I'm going to store the pointers which will be indicating that where is the next record stored. Okay, I have two things. I'll be storing the actual data in the first column, and second one stores the pointer fields where the next record is being stored. If initially everything will be initialized to -1, initially this next column all the pointers will be initialized to -1, indicating that they are not pointing anywhere. Now first time I have Adams 20, I'll go to 20. Yes, no record is there, I'll insert here. Next I have Bates 21, directly I'll move to 21. Yes, it's empty, I'll insert it here. And Coles I have 20. So I'll go to address 20, but already somebody has occupied this. Now what do I do? I check for the next successive location. Where is the next successive location? 22. Where should I put this 22? 22 I need to put it here because 20 was the home address generated by both Adams and Coles. Since Adams is already exactly stored at its home address and 20 is also Coles, the next, so 22 means it is giving the pointer position where the next record of the same home address is stored. See, 22. Coles is there. Now Dean 21, I'll go to 21. 21 already some record is stored. So what do? Check for the next successive location. Checks for the next successive location. Successive location is here. As per your progressive overflow, this 23 location, whatever the position, I'm going to store it here. I'm going to store it here because the home address of Dean was 21. Since the space was not free there, I basically go here and I'm going to store its position value here as 23, indicating that okay, Bates is here. So the where is the next home address? Same home address generated record. It is present at location 23. Okay. So now again I'll be storing evens. Evens I want to store 24. I'll go here evens. Yes, evens I have stored here. So no, evens is not pointing to any other location. No other further records are stored in a in the form of a linked list. Actually, it's in the form of a linked list. See, Adams I have stored here. Now 22. 22 tells me that where is the next record following the same home address. See, it is here. 25. See, it is nothing but in the form of a linked list. It is being stored. Okay, where each node will be having a minimum 2 fields. One stores the data and another one stores the link information. See, like this, 22 is nothing but a link information of the next record. 25 is the link information of the next record. Where exactly? If no further records are there, the last link field of the last node usually will be 1. Okay, so now this is how you have stored the records using the overflow progressive overflow concept. This is how you are stored using the chained progressive overflow. Now, in order to compare the search length that basically a progressive overflow takes and chained progressive overflow takes, definitely the search length taken by a chained progressive overflow is very less, that is 1.7. Why? Because you are getting easily the link field. You need not additionally make the additional searches. So whenever you go to that particular home address, if it is found, you will tell that search length 1. If it is not found, directly you'll be jumping. You'll be jumping directly to that address field and you'll tell that definitely it is there or not. Definitely compared to the search length of a progressive flow is very less. So this is how it has a better advantage compared to the progressive overflow. So now let us consider a problem. Suppose that Dean home address is 22. Since Coles is there, this couldn't have a link to Dean starting at the home address. This is one specific problem we are taking with respect to your chained progressive overflow. So how to deal with this? Okay, so we can make use of a concept called as a two-pass loading. So what is the two-pass loading? So in the first pass, what basically I'll be doing is I'll be storing the records which exactly fits at their home address. I'll be storing all the records in their appropriate address where they exactly fit in their home address. So Adams, I'll go to 20. So yes, nobody is there, I'm going to store here. 21, I'll go to 21, nobody is there, I'll store it here. 20, already Coles 20, somebody is already occupied, so I am not going to touch this Coles. This is an overflow record, definitely I know. Dean 22, I go to Dean 22, nobody is there, I'll store it here. 24, yes, nobody is there, 24. And this is how during the first pass your progress overflow looks like. So initially they're not pointing to anything. Now I'll make a second pass. I'll go through the table for the second time. After going through the table for the second time, I look for the overflow records. So which was the overflow record? Coles 20. I'll go to 20. See how this operates. The previous example. I'll go to 20. So 20 was the address of Coles. Since I cannot store Coles here, I'll store it in next successive location and I'll store the address field of this in the link field of the first record. See 23. And Flint 20. So I cannot store it here. Again, it has given me an address this here. I'll check for the next successive location, store the link field of that in this. So this is how basically we make use of two-pass loading in case of a two-pass loading in case of your chained progressive overflow. Okay. So hope so you have understood till now. Coming to the next one is nothing but chaining with separate overflow area. Chaining with separate overflow area. Now, all the overflow records, you're going to separately store it in a separate area, and that separate area is nothing but called as the overflow area. Okay, see, this is a primary data. So the primary data, since Adams was the first record, it was not overflow record, nothing, it was empty. So you have stored here, weights you have stored here, events you have stored here, everything. Suppose calls has also generated the same address. Since there was no space here, that overflow record, you're going to put it into the overflow area, and the pointer position where exactly it is stored, that pointer position you're going to store it here. Okay, suppose say next I have Flint. Flint is also having an home address 20. Here I cannot store. I'll go to 0th location. Yes, here also it is occupied. So if it is occupied, I need to check for the next successive location, whichever is free. So this location is free, I've stored here. Now the the field, what is the field where exactly the Flint is present, that pointer value I need to update it here in the link field of the codes. Okay, if it is no, it is further, if it is not pointing to any of the records, then make it as -1. Here also, if it is not further pointing to any of the overflow records, make it as -1. See here. So this is how chaining with separate overflow works. You'll be having a separate overflow area and you'll be having a primary data area. So primary data area is the one where you'll be storing the records which will exactly fit at their home addresses, which exactly fits at their home addresses. Overflow area is the area where we will be storing the overflow records. Okay. Coming to the last one, scattered table. It is nothing but, instead of last example, you had one separate overflow area and separate primary area. Here you will be having an index file and you will be having a data file. So whenever you are storing 20th address, where exactly you should go? You should go to the 0th area. And again, Coles also was generating this. Wherever the spaces are there, you'll be having a link thing. So now this is nothing but your separate file called as a data file. And this is nothing but called as an index file. Index file only will be storing the starting index where those particular records have been stored in the data file. And your data file is is basically works similar to the previous techniques what we have used. Okay, so this is the end of your hashing. Okay, we'll stop here and we'll continue in the next class. So now I request all of you to enter your USN into the chat box.